I'd like you to imagine for a moment that you are swinging a rock tied to the end of a string in a circle. How can we describe the motion of this object? Well, if I want to define the velocity or speed of this object as it makes its way around the circle, I can think about the definition that I had for speed earlier. And in this case, I'm going to use velocity and speed interchangeably. We're assuming that the object's just traveling one way, so either clockwise or counterclockwise as it goes around the circle. So we don't need to worry about the difference here between velocity and speed as we define this term. So we defined speed earlier, right, as the distance an object travels in a certain amount of time. That was our definition for linear speed. Well, if I think about this rock making one full, we call it a revolution, or one full way around the circle, then how far did it go? In other words, what distance did the rock travel if it went all the way around the circle? Well, we can call that the circumference of the circle, right? It's made one full circumference. And if I know, right, let's call the radius of this circle, or the length of this string, let's call that r. If the circle has a radius r, then I know the distance around that circle will be 2 pi r, right? That's the formula for the circumference of a circle. I can also say that that would be the same thing as pi times d, where d is the diameter, which, as a reminder, is equal to 2 times the radius, right? And as far as time goes, we actually can call the time that it takes to make one full revolution a specific term, and we're going to call that big T, or time period. So I'll show that here for time, a big T. Now, again, I just said this, but let's define T separately. T would be the time it takes in seconds to make one revolution, or one full way for that rock to end up back where it started around the circle. So if the time period is the time that it takes to make one full revolution around the circle, we can also define a quantity called the frequency, which is actually just the opposite of time period. It's the number of revolutions that it makes in 1 second. And so you'll see this sometimes defined as 1 over t. Now, before we define the centripetal acceleration of this object, I want to explain a few things. When I defined the tangential velocity for this object, or the speed of the object as it travels around the circle, what we need to understand is that if we were to let go of this rock, what would happen to it, right? Let's say you were swinging this rock in a circle, and all of a sudden you let go, or you cut the string. What direction would the rock start traveling in, right? If you don't believe me, go ahead and try this yourself. What'll happen is the rock will just continue traveling in a straight path in whatever direction it was traveling right before you let it go. And so the reason we call this a tangential velocity is because the velocity of this object at any point around the circle is tangent, or perpendicular to the circle at that point. So if I show that, that would look like this, right? Tangential velocity would be here. Let's say the rock is over here, right? Which direction would the velocity of the rock be pointing? Well, it would be pointing tangent to the circle, or in this direction, right? That would be my tangential velocity. It could also look like this. If it were at the top of the circle and I let go, the rock would just keep moving in a straight line in the direction that it was traveling in at that point. And so the tangential velocity of the object, the one we defined previously, always points tangent to the circle. But if we think about what's happening right now, the velocity is both magnitude and direction, right? We defined that previously. Velocity is a vector quantity. My velocity is not changing in magnitude, but it is changing in direction. Every second, the velocity is changing directions. And so by definition, we are accelerating. Acceleration is defined as a change in velocity. And so if I'm changing the direction of my velocity, even if I'm technically going at the same speed, I am accelerating. Now, to understand the direction of acceleration, we can show two velocity vectors side by side, like so. I'll go ahead and show another velocity vector here in blue. That would be the tangential velocity at this point, right? And if I were to subtract them, or find the change in velocity, I can actually subtract vectors by putting both of the tails together, and that would look something like this. Not quite to scale here, but not bad. Okay, there we go. So this would be my, well, let's call this VT2, and we'll call this first one VT1. If I were to look at the change in those velocities, if I draw the resultant vector now, how would that look? Well, if I draw from the head of one to the head of the other, it would look like that. That would be the change in velocity, or in this case, the net velocity, the resultant vector of my two velocity vectors there, if I were to find the change in them. So what you'll see is if you keep doing this, right, the velocity vector is always going to point, the change in velocity will always point into the circle. This is the direction of the acceleration of the object. It is accelerating into the circle. So what I say is the centripetal acceleration, right? This is the direction of the centripetal acceleration. It must be, because that is the direction of my change in velocity. Now we can quantify the centripetal acceleration of an object in terms of its tangential velocity and the radius of the circular path that it takes. I'm going to skip the derivation here, but if you'd like to see this derivation, please take a look at the OpenStax physics textbook for a full derivation of how we got the formula for the centripetal acceleration of an object. But for now, the centripetal acceleration of an object can be calculated by taking the tangential velocity of that object squared and dividing it by the radius of the circular path that it takes. All right, now that we can describe and quantify the motion of objects traveling in a circular path, let's take a quick look at why objects move in a circular path in more detail. So as we saw with our examples, there's always a force causing an object to move in a circular path, right? There's some force that's redirecting the motion of this object to keep it traveling in a path that is not a straight line. And so we can call this force, or in some cases, there are multiple forces causing this, pointing into the center of the circle, the centripetal force. This is a name that we give the net inward force pointing into the center of the circle. This is not a new force. I want to be clear about this. The centripetal force is not some new force that we're creating here. It is just a name that we give to whatever force or forces are causing the object to continue moving in a circle. Centripetal means center seeking. So it's a name that we give the force or sum of forces causing circular motion. In this case, I'm going to use this sigma notation here, that the centripetal force is equal to the sum of the forces pointing in. That will be how I use this in calculations. I will show it as the sum of forces pointing into the circle, because that's what it is. On the left-hand side here, we see those examples again, as we saw before. Tension, right? Tension can be a centripetal force here. That is the tension in that chain. Friction, in this case specifically, right? Static friction can also act as the centripetal force. We would give that the name of centripetal force. The normal force, right? The normal force here can act as a centripetal force. Gravity can also act as a centripetal force. So again, these are all centripetal forces. So the centripetal force is just a name or a label that we ascribe to a force causing circular motion. And we can apply Newton's second law just like we did before. The net force in any direction is equal to the mass of the object multiplied by the acceleration of that object in that direction. And so earlier I said we call this the centripetal acceleration. I'll also call this a inward, or the acceleration pointing inward into the circle as we defined previously. And again, multiple forces can either work together or against each other to create this centripetal force. So actually, if you take a look at this roller coaster here, this is a roller coaster turn, which still constitutes circular motion, where the radius of that circle, the center of that circle, I should say, is actually in the middle right here, right? The roller coaster, the normal force is actually not pointing into the center of the circle. It's pointing away from the circle. What force is pointing into the circle here? Well, that would be the gravity of the object. So in this case, we actually have two forces that we'd have to consider. The normal force and the gravitational force work against each other to create this net force inward, which we call the centripetal force. So we'll take a look at some complicated examples where we have multiple forces acting as the centripetal force. But for now, just know that it's a name that we give the net inward force pointing into the circle.